Okay, so I want to apologize in advance because this one's going to be a little bit long, but it's an important one. So let's get on it. Natural disruptions to ecosystems. So a lot of this course we're going to talk about how humans impact ecosystems and disrupt them, and the environmental problems that result from that. But it's important to understand that the biological systems on our planet are adapted to handle these changes because they do happen naturally as well. Anytime there's a disruption to an ecosystem, the animals that live in that ecosystem, well, all the organisms, have to either adapt to the new conditions, migrate away to more favorable conditions, or go extinct in that area. Now, these these different types of natural disruptions can happen at different levels. They can be localized, like say a forest fire, a flood, a volcanic eruption. They can be at a global level of say, an ice age or meteor impact. So they can happen at all different kinds of scales, both in terms of spatial scales on a planet and temporal scales over periods of time. So they basically come down to either period. They can be random, they can be periodic, or they can be episodic. So let's see what each of these means, basically. So periodic means they happen fairly regularly. You can almost count on them occurring. So these would be things like annual flooding of a river, El Nino events that happen every, say, 5 to 7 years. These are fairly predictable events that still disrupt the ecosystem because they're not the normal of the ecosystem. Episodic ones would be ones that happen less frequently, but they still happen with a certain regularity to them. And a good example of this would be ice ages. They happen over the course of thousands of years, and yet they have a certain pattern with which they happen. And then we can have just random ones. Okay, sorry, still talking about episodic ones. So if we look at ice ages, we can. There's ways of mapping them out, which we'll talk about. But basically, we can say here we are today. Technically, we're in an ice age. Temperatures were colder in the last, say, 10, 20,000 years. They were warmer, then they got colder, then they got up to about where they are today, then they got colder, then they got warmer, and so on. So you notice it's almost like looking at an EKG, and there's a certain pattern to these temperature changes. But keep in mind, each one of these temperature changes is going to cause major disruptions to global ecosystems. And then we have random ones like, impactor events, things that we just can't count on, some new disease, whatever. There are things that happen that are random that make wide-scale changes to ecosystems. The largest ones, the largest disruptions are those which change the climate of the Earth, because when you change the climate of the Earth, you essentially affect the distribution of all of Earth's biomes, right? Because they're linked to temperature and precipitation, which are linked to climate. And so if you change the climate, you tend to change all of Earth's ecosystems. And life has adapted to this, but these changes are significant, and they result in some fairly predictable responses from the life in these biomes. So naturally occurring climate change. We hear about climate change all the time today because humans are causing climate change. However, climate change has definitely occurred in the past. From that graph you just saw, we know what happens. Well, what causes it? Well, it can be a variation in the output of the sun. It could be due to the wobble of Earth's axis, which doesn't always point in the same direction. It could be due to changes in the way that ocean currents distribute Earth's thermal energy, or it could be the result of volcanic activity, which essentially block out solar radiation, reducing the overall temperature of the atmosphere. So let's talk about solar output. We tend to think of the sun as being a fairly stable thing, and it is. I mean, it's been going for 5 billion years, and it will probably go for another 5 billion years. But after Galileo discovered sunspots in the 1500s, people have been fascinated with them, and they've studied them quite well. And what we found is that there have been times when the number of sunspots, which are located, which are not located, which are located on the sun, but which are associated with solar activity and temperature. There was a period of time called the Maunder Minimum that happened in the 1600s. There was very few of these noted. And in that same time period, glaciers on the planet advanced. There was snow in London in the summertime. And so it seems that the output of the sun definitely caused variations in Earth's climate, and that led to natural disruptions in ecosystems. But fortunately, the sun doesn't change that much as far as we know. Now, the wobble of Earth's axis was also because of precession of equinoxes. Basically, what happens is uh, the Earth right now, our North Pole is pointing at the North Star Polaris, but it doesn't always. In the past, it pointed at the star Vega. There's ways of mathematically working out where it pointed, but the real point of this is it changes where Earth's continental land masses are relative to incoming solar radiation, and that has a lot to do with how much energy is going to get absorbed, and that in turn changes the climate, which changes, where biomes are located. Ocean currents are really important. We'll study them on their own this year, but basically, here's a map of Earth's major uh, ocean currents. And what we find is there are these gyres, we call them. And essentially, what they do is they carry warm water from the equator up to the north, keeping the upper latitudes warm. They carry cold water south to be warmed up. And essentially, if it wasn't for these currents, the equator would be much hotter than the rest of the planet, would be much colder. And so what happens is if there's any alteration in these flows, it's going to result in huge changes in the distribution of energy on the planet, which is going to result in climate change, which is going to result in changes in biomes and natural disruptions that are going to lead animals to either have to adapt, migrate, or go extinct. Now, it's worth noting right now, there is a major concern that the North Pole, which has an ice cap, is basically affecting the flow of this particular current. Now, what happens is if it melts away, the worry is this water is going to move this way and it's going to change this gyre. And when it does, we have no idea what's going to happen, but we know that removing the polar ice cap due to climate change is going to change the distribution of this, and that will lead to an even more significant disruption in ecosystems. Also, too, again, something we'll study later in the year, the surface of the Earth isn't static. It's constantly moving. There are internal movements in the Earth that cause the surface to move around. And the configuration of the continents as we know them today is not what they've always been. So clearly, if you move these, two things happen. You change the flow of these currents, and you also change where the continents are relative to the majority of the sunlight. And both of these things lead to climate change. And then we have volcanic eruption. It's been well documented that large volcanic eruptions like Krakatoa and Pinatubo, they definitely basically put material in the upper atmosphere up into the stratosphere where it doesn't settle down for a long time. And this then reduces the amount of energy coming to the Earth. It cools the Earth's surface, and that leads to climate change. Another thing that can happen, though, is if you have lots of volcanoes, not necessarily major ones that put plumes up in the stratosphere, but if you have there have been time periods in Earth's past where volcanic activity has been more common. Well, one of the things that comes out of a volcano is CO2, and CO2 is a substance that makes the Earth warmer by trapping infrared light. And so that's another way that volcanoes can result in climate change. So they could either cool them through massive eruptions or heat the world through increased CO2 production. Now, we don't have time machines, but scientists are able to piece together past climates in two main ways. You can look at the distribution of fossils. So if you find tropical fossils in northern latitudes or woolly mammoths at the equator, you kind of know that there's been some changes in the climate. Another thing we can use is oxygen isotope ratios, which is kind of cool. I'll try to get you to understand that. It's neat. You don't probably have to know too much about it, but it's worth knowing that it is a technique we can use. So the distribution of fossil species, basically there have been times in the past the world was warmer, and so we find these tropical fossils of plants and animals much closer to the poles. During glacial periods, we find these fossils that are associated with, say, the taiga or the tundra much closer down into the lower latitudes. And so we can definitely use fossils to map out past climate changes. And we can use oxygen isotopes. So oxygen is element 8. The most common isotope is oxygen 16. But there's another isotope of it that has 2 more neutrons called oxygen 18. So oxygen 18 is still oxygen, but it's just a heavier variety of oxygen. It's naturally occurring, but what happens is water containing the lighter one, it basically is able to evaporate more easily, and it's able to stay airborne for longer. The heavier one is harder to evaporate, and it doesn't stay in the air as long. It's just heavier. And so what happens is we can analyze ice samples at the poles. We can analyze the oxygen that's present in the shells of organisms. And by doing this, we can look at these ratios of O16 to O18 and figure out what past climates were. Pretty cool, right? All right, so basically it goes like this. Again, you're not expected to be able to display a strong understanding of this, but I just want to point it out. The idea is the water, as water evaporates, the O18 is heavier, so it tends to not make it all the way to the pole. So when it evaporates, most evaporation happens near the equator. It doesn't make it to the poles. So what makes it to the poles is sort of O18 depleted, so more O16 is found up here. So what we find is the snow in Antarctica or the poles is going to have about 5% less O18 than ocean water does. And that's because it can't stay in the air as long. And then meltwater from this is also depleted in this. So organisms found here are going to have lower ratios of this. So basically, people have been able to make the argument using these ratios of O18 what the temperature was like in the past. And it does seem to be a pretty strong argument. Here is a temperature graph of the Earth throughout the Cenozoic. That's the time period that followed the death of the dinosaurs. So the dinosaurs died back here at the KT boundary when the meteor hit. Here's today where we are. 0 meaning this is normal temperature, so 0 degrees above normal. We see it ticked up a little bit here because of global warming. We'll cover that later. But basically, we know that about 10,000 years ago was the end of the last major ice age. We're still technically in an ice age, and ice age just means that you have ice caps. Well, I should say that you have continental ice near the poles. And so basically, 20,000 years ago, it was much, much colder. But then there are these periods when it got warmer than it is now, and then cold, and then warm, and then cold. So we get these periodic changes. And then as we go farther back, from this point here, from about 3 million years ago backwards, there was only one event we know where it got as cold as it is today. This one right here. But other than that, I'm sorry. Here's the KT boundary here. I was mistaken. Okay, so this is where the dinosaurs went extinct, and then we know we had some cold back here from fossil evidence. So ice ages technically are just periods of time when you have continental glaciers. That means glaciers that cover large areas of a continent. These glaciers tend to be like 1,000, 2,000 meters deep. Right now we have them in Antarctica and Greenland, and I think there might be one ice, I'm not sure, but basically that means we're technically currently in an ice age, although we are rapidly moving out of that because of climate change. Now, ice ages are a good example of something that comes up on the test sometimes, which is called a positive feedback loop. Okay, so here you go. Basically, ice ages can be triggered by an event in which you get a particularly heavy scenario. So first of all, let me just say this. A positive feedback loop is a condition in which there's a change that occurs, and the outcome of that change accelerates the rate at which that change occurs. So the change causes more change, causes more change, causes more change in the same direction. We call that a positive feedback loop. This is a classic example of it. So here is this sort of current configuration. This is Greenland. This is the North Pole. This is northern Canada, I believe it is. And so what you have then is sunlight reflects off snow and goes back into space. We call this albedo. I don't think you need to know that, but it's not a bad word to know. So albedo is the energy lost through reflection. So the more albedo there is, the less energy is getting absorbed by the Earth. Well, that means, so let's just say we get a year where there's a particularly heavy snowfall. We get a lot of snow over the northern latitudes in, say, Siberia and Alaska and northern Canada. Well, what would happen then is more snowfall means more albedo. More albedo means more light energy is being reflected into space, so the temperature of the atmosphere goes down. What does this do? Well, it causes more snow to happen, which causes more albedo to happen, which causes the temperature to change more. And so you get this positive feedback loop that can lead to advancing continental glaciers. All right. So that's one mechanism by which these could happen. Now, 20,000 years ago, much of the world was covered by these continental glaciers. We know from fossil evidence. Now, what that means then is the biomes that we know today were not where they were. Where they are today is not where they were then. All right. So the taiga would be down here. Yeah, you'd have tundra. You'd have taiga all the way down into here. So as these ice sheets grow and shrink, the biomes grow and shrink with them, and the animals in there have to either migrate, adapt, or go extinct or evolve. Okay, And so these natural disruptions that happen on the scale definitely cause these changes in life in Earth's ecosystems. Now, ice ages occur with fairly regular periodicity. You can see here, it looks like like I said, like a heartbeat graph. But basically, we know these glacial periods very well. This is basically the current temperature, and we see it goes down, it comes up, it goes down, it comes up. These natural disruptions cause organisms to have to adapt. Now, one thing that's worth noting, though, is this ice, the water for this ice that piles up on these continental ice caps comes from the ocean. So what that means then is that the sea level has to go up and down. Now, right now, sea level is moving up a little bit, and that's causing a displacement of organisms. But if we look in the past, what we find is that sea level has been quite a bit lower in the past. Look at this, up to like 100, 120 meters lower than it currently is. And there have been times when it's been 8 meters higher than it currently is. So anytime you change sea level by 100, 120 meters, you're going to expect to have a very interesting situation. Most continents, if you look on Google Earth, you'll notice this sort of light blue area. This is called the continental shelf. So the continent actually extends out to where it turns dark. It's just right now it's flooded. But what happens is, so here's our continental shelf. This area here is this area here. If you drop sea level 100 meters, all of this becomes exposed. Now we just have this land that was devoid of terrestrial organisms that then will have to have organisms move into it in a process called succession. Now, another thing I think that's the end of the slide. Just sorry it's so long. Another thing to keep in mind is that these glaciers grow and shrink. The water level goes up and down, and this sometimes lead to the formation of land bridges. So these land bridges have led to, say, the ability of organisms to migrate from Asia into the Americas. So right now here is the continental shelf, which is underwater, but there was a land bridge before which allowed them to migrate across. And when that happens, you end up with adaptive radiation. You have all these new species move into an area and populate any niches that aren't filled. So you can see that just the natural changes in Earth's, particularly climate, lead to a lot of changes in ecosystems. And this is a normal process. The thing is, as humans, we tend to cause this to happen at a much faster rate, which is more difficult for organisms to adapt to. But that's for a later lesson. Sorry this was so long, but thanks for watching.